Dear students, today I am giving the fifth video on topology, and we start with the theorem which is a continuation of the fourth video. Their statement: let x alpha to alpha in index set be an indexed family of topological spaces, and for each alpha in the index set E alpha subset or equal to x alpha. There are two parts to be proved. Part A, if A alpha is a closed subset of x alpha, then pi A alpha is a closed subset of pi x alpha. Part B is pi A alpha closure is equal to pi of A alpha closure. There are two parts, that is parts A and B we have to prove. Coming to the proof of the first part, as part A. Suppose that A alpha is a closed subset of x alpha for all alpha in index set. To prove that, what do we have to prove? We have to prove that pi alpha is closed. So, in order to prove that pi alpha is closed in pi x alpha, it is sufficient to prove that pi x alpha minus pi a alpha is open. Okay. So, take x, what is x alpha index set be an element of pi x alpha minus pi a alpha. This implies x alpha is not an element of pi a alpha, correct? But pi a alpha is the intersection of all such pi alpha inverse a alpha, where pi alpha is a projection map. This implies x alpha is not at all an element of intersection of pi alpha inverse a alpha. This implies there exists beta in the index set such that x alpha in index set is not at all an element of pi beta inverse A beta. Therefore, pi beta of x alpha or alpha index set is not at all an element of A beta. This implies x beta is not an A beta, which implies x beta is an element of capital X beta minus A beta. Put u beta equal to x beta minus A beta. Then u beta is open and small x beta is an element of u beta. Put v equal to pi beta inverse of u beta, where pi beta is a projection map. Then v is open and small x is an element of v. Also v intersection pi a alpha is equal to phi. Since beta the factor of v is u beta, what is u beta? X beta minus A beta. What is beta the factor of pi a alpha? That's what? A beta. Let's say we are able to write v intersection pi a alpha, that is equal to phi. And this implies v is subset or equal to pi x alpha minus pi a alpha. That is x small x element of v subset or equal to pi x alpha minus pi a alpha, which implies pi x alpha minus pi a alpha is open in pi x alpha. This is open in the sense pi a alpha is closed in pi x alpha. That is what the first part of the theorem. Part A is proved. Now coming to part B, that x alpha in the index set is an element of pi E alpha closure. That beta in the index set, to prove that x beta is an element of A beta closure. Let u beta be a neighborhood of x beta, then pi beta inverse u beta is a neighborhood of x alpha, where alpha is in index set. This implies pi beta inverse u beta intersection pi a alpha is not equal to phi. This implies u beta intersection A beta not equal to phi. That is, every neighborhood of x beta intersects A beta, which implies x beta is an element of A beta closure. Since this is true for every beta in the index set, it follows that x alpha is an element of A alpha closure for all alpha in the index set. This implies x alpha in the index set is an element of pi of or pi A alpha closure. Therefore, pi A alpha closure is subset or equal to pi A alpha closure. That is what the first result. We get the other side. On the other hand, let X alpha be an element of pi A alpha closure. This implies X alpha is in A alpha closure for all alpha in the index set. Let W be a neighborhood of X alpha in the index set. Then there X is a basis element pi U alpha, where U alpha equal to X alpha for alpha not equal to beta 1, beta 2, etc. beta n, and U beta I is an element of tau beta I for all I equal to 1 to n, such that X alpha is an element of pi U alpha, which is subset or equal to W. Let X beta I is an element of U beta I, where U beta I is an element of tau beta, it's open, and X beta I is an element of A beta I closure for I equal to 1 to n. This implies U beta I intersection A beta I not equal to phi for I equal to 1 to n, which implies pi U alpha intersection pi A alpha is not equal to phi. Or in other words, W intersection pi A alpha not equal to phi. That is, every neighborhood of X alpha, alpha in the index set, intersect pi A alpha, or X alpha is an element of pi A alpha closure. That is, pi A alpha closure is subset or equal to closure of pi A alpha. That is what the result 2 from 1 and 2. It follows that pi A alpha or closure of pi A alpha, correct. Pi A alpha closure is equal to pi A alpha closure. Closure of pi A alpha is equal to pi A alpha closure. That's all right. Then coming to the next part, that's what the weak topology and the product topology. And definition, first definition, let X be a set and let X alpha to alpha in the index set be an indexed family of topological spaces, and for each alpha in the index set, F alpha from X to X alpha be a function. The weak topology on X induced by F alphas or alpha in the index set is the smallest topology on X for which F alpha from X to X alpha is continuous for all alpha in the index set. Idea is the weak topology on X induced by F alpha is the smallest topology on X for which F alpha is continuous. That's the definition. Remarks are given. First remark, if we consider the discrete topology on X, then F alpha from X to X alpha is continuous for all alpha in the index set. And second remark, if X equal to pi X alpha and the weak topology on X induced by pi alphas is the product topology on capital X. And that's all about this part. And 5-page notes are there. Watch the video properly, check the notes, and any doubts are there means please mark it. We can discuss in the next class.